Hello everyone, welcome back to the EPT. Today we are going to start with the question solving as promised in the previous session. So today we'll be starting with the machine learning problems, and I have already told you that what we are going to start with. Okay, so let's see. Let's just check out. Am I audible? Is it fine? I hope I'm visible. Let me also check, and then we'll be getting started within just 2 minutes. Hmm. Yeah, let me just check. Yes. So audio is fine. I guess video is fine. Today you guys can see me as well. So it's okay. Let's get started. I hope you understood what I shared in the last session with you, that how you can actually work on yourself to improve upon what you have done until now, and to avoid your panic situation, to understand how you need to proceed further in these short duration of time, whatever number of days you're having. Okay, so as mentioned, now we'll be starting with our first day, and I hope you remember we talked about what we are going to talk about. So this is my intro as usual. So today's lecture would be about linear multiple polynomial and logistic regression plus the regularization we are having now. So as I promised, there will be three parts always to whatever I'll be presenting. Now, if I talk about the first thing, would be the cheat sheet, which you need to understand, which you should remember. Okay. The second would be the problem solving, which we are going to have, and then third part would be a small guidance which I have prepared for you for every session which we are going to have. Okay. So starting with the cheat sheet, so I hope you understand the simple linear regression, in which case I'll be having only one independent variable. A model is given to you. We have a solution which is which is like from the closed form solution which we are having, x transpose x inverse and then x transpose y. Uh, I'll get beta. Beta over here means I'm talking of the vector beta naught and beta 1 altogether. We can also solve it using the gradient descent by minimizing the mean squared error we are having. Okay, so just basic around it. What exactly is the cheat sheet? We don't really have a good time to basically spend upon the entire theory, so just some minimal idea over here. Now, similar to the simple linear regression, we had just one independent variable over here. Over here we are going to have a number of features or independent variable, and which, like you can see over here, like b naught plus beta 1 x1 plus beta 2 x2 and so on until p number of features if we are having. The solution would be again can be derived from the normal equation form which we are having, but the gradient descent solution becomes important if the data is large. Okay, or if x transpose x becomes non-invertible. In that case it becomes important. We shall go by the gradient descent approach. Now, okay, I guess it, yeah. Now the other is the polynomial regression. What do we have in that? Is we had something on like simple linear regression or the multiple linear regression. We just extend our feature space by adding the new polynomial degrees to the same features we had, and then we try modeling that. Okay, that's how we have the polynomial regression. And like it's mentioned, how what do we do in that case? So again, we can use the normal equation similar to the multiple linear regression, or we can use the gradient descent as per requirement, as I mentioned for the multiple linear regression. Coming to the logistic regression, as the name suggests, it's regression, but being used for classification purpose, because the way we actually try fitting is regression is being used over there, but overall it is being used for the classification problem only. And this you can see over here, the model is log of p upon 1 minus p. So it is basically log of odds, which is being modeled as the linear combination of your features we are having. Okay, that's how we model it. And if you just would like to calculate the probability, then you get the normal equation which is being used for this modeling, which is if you take you take this what should I say, p upon 1 minus p. If you take the log on the other side, or basically take anti-log, what you'll be getting is e to the power b naught plus summation of all that, and giving you p equals 1 upon 1 plus 1 plus e to the power minus the same equation you're having. So this is not going to have a closed form solution. You'll be using basically the gradient descent most of the time. The other method, just for the understanding purpose, you need not require that understanding, but yeah, we use gradient descent in that case. Okay, so that was about the regression, which is present in our syllabus. Now the next thing is the regularization, which we'll be using for most of the modeling techniques, but this is the first phase where we actually see the regularization technique, where we just add on something on addition to our objective function, which is going to be lambda times of, if I had weights like beta over here. So if I'm taking the summation of all the beta squares, in that case, it's a ridge regression or L2 regression. If I'm adding modulus of these beta, in that case, it's lasso regression. Okay. And for the ridge regression, you again have a closed form solution written like this. The way we derive it is not in, like, I don't know, like whether you have done it or not, but need not really get into those. But yeah, something you should remember that we have a closed form solution for this as well. But we do not really have a closed form solution for the lasso or elastic net. Reason being, the lasso, if you just consider that, we get a modulus function over there, okay, which is basically non-differentiable, and hence we have to like we can't really optimize it directly. Hence, we have to use gradient descent over there rather than any closed form solution, which we do not really have. So that was overall idea around what we talked about for the cheat sheet part. Now we'll be solving problems as promised. Let's get started. So yeah, what is the primary goal of the linear regression? I guess very easy question, as I mentioned. So like we'll be having mixed bag of questions. It would not always be very difficult question, or not always easy, and some intermediate as well. So what do you guys think? Whosoever is watching, you can just take some, I can take a pause, or you can just pause the video and then think about this. What should be the answer over here? And just to give you the context over here, the questions are being derived from multiple resources out there. Okay, when I say multiple resources, IIT, IISc, some of the foreign university, I would not really bring very difficult questions from there, but something which is relevant to us, something tricky, those are being considered over here. And apart from that, some standard books we are having. Okay, again, a relevant one. Okay, because not every question needs to be solved. That might be like a little out of the way. So yeah, over here we have a simple question. What do you think can be the answer? So we have an answer. What's going to be that? So if I just talk about that, it's going to be, okay, I guess I can't type. Is it not possible to write? Let me check. Can't I write it? Okay, so I guess we can't really write, but I can definitely help. I would not really be needing the pen to solve the problems today, because I would give you the idea how, without even solving the problem, how you can think about it and can really get the answer closer to what it should be. Okay, so over here, if I just go by option, what exactly is shown? To summarize the data using principal components? No, nothing like that. To maximize the correlation between variables? Nah. To find the average values of the dependent variable? Is it so? To minimize the sum of squared residuals between observed and predicted values. And that's what is our objective function is also over here. Okay, so this is the correct answer, option number D. Okay, so I hope it was clear. A very simple question we had. Yeah, this is an interesting question over here, which might make you think that you actually need to use pen and paper to solve this question. But trust me, I'll not be only just telling you that how you should approach a problem, but would also be telling you how you can minimize the effort required to basically answer the question. Because trust me, machine learning is really a difficult subject with respect to the higher studies. and that is being used as a prerequisite in your gate exam. So it's a very simple thing, direct to you, that they would not really be getting into too much of the details or too much of the difficult things. They would really love to know how you can use the basics and still be able to solve the problems, cover the things easily. Okay, so that's the intention with my question sheet as well over here. So if you just look at this, it's very simple. We are having this, we wanted to learn the function of the form ax plus b. So that means x, we know what is it. Fx is my y. I just need to learn what is a and b going to be. So everything is like you can just read by, but we understand what it should be like. So I need to just fit in a line over here. Now I would like you to think over here, think about this. Can you see some relation between x and y directly? Do not use a pen and paper. Just think about this. 2 is something like given, like some 9 is there in front of 2. In front of 3, there is something 12. In front of 4, there is 16. In front of 5, there is 19. In front of 6, there is 21. Just think about this. Like, what do you think is going to happen over here? So if I just think 2 4 times, like 2 into 4 is 8, I'm getting something closer to 8, which is 9.9, not too closer. Let's check that up. 3 into 4, 12, something closer, yes. 4 into 4, 16, yes, closure. 4 into 5, 20, something closure, 19, yes. 6 into 4, 24 over here. So over here, it seems like something is off. So in case of just last one, we can see it's literally a little far from what we are expecting. But the others are actually fitting very closely to what we anticipate. So it should be something like y equals 4x. But we need to find out a and b. Now, what to do in that case? So if I can't really add, like can't really have 4x and need to split it up, can I have something like what should I say, something closer to that? And what can be that? Simply 3x plus 4. Now why am I saying you just check it out? So whatever you will be getting is going to be that same value only what you will be getting over here. So something like that, if I want to write, which I can't, sorry, over here I am not able to use my pen and paper, but let me just try that. Also, if I can just open it up for your writing purpose as well. Just wait, I'll share my screen, because I guess I'm not able to show it over here. So yeah, let me just share my screen. Okay, so right now I'm assuming that you are able to see my screen clearly. So I'll just go to that particular problem that we had over here. If I just talk about this one, how we can really solve it is, as I mentioned, let me just, okay. So what I'm saying is, it seems like y equals 4x seems to be something fitting over here. Okay, but not every time over here. And you can literally like solve using the equation you're already having. You can simply use that also to find it out. But just giving you an idea over here, if you can't really fit it up, what is the closest solution which you can think of? Is it 4x plus 1, or is it y equals 3x plus 4? Just think about this. Just think about this, what we are actually writing over here. So what I wanted was, I wanted to add like just one extra number which can contribute a number of 4 over here, because I was not really able to bring 4x directly. So can really this one help over here? Can you just check this out? Either of these would be really able to help you or put you closer to this. And in that case, once you understand, you can just verify which one is going to give you the lesser answer, and then you'll be having the answer. Okay. And the other way is directly going by the way, which is like a general method. solving, you can use simply the approach over here by minimizing your mean squared error, and you'll be having the final solution for A and B also over here. So if I just go by this particular approach, the correct answer is going to be 3x plus 4 over here. Okay, I hope you guys are getting. If you have any doubt, you can just always message me over here in the chat. If not, it's okay. Let's keep on going. Okay. Now I'll be going to the second question. What we are having? Sorry, third question. Second is done. So you can always solve by the general method, but I'm not here to talk about what you already know or what is like basically everyone is teaching. I'm over here to tell you exactly that what are the extra things you can just use to basically solve a problem. Okay. Again, theoretical question over here. Which technique can model non-linear relationships between input and output variables? So if I just go by the basic idea for the linear regression, we know that it generally models the linear relationships only. To bring up the non-linear, we have to introduce some kind of a functions, and the other way to think of a function is always a polynomial function, and we have a polynomial regression. So the answer to this problem becomes easy polynomial regression. I hope you're understanding. If you will be having any doubt, do let me know. Okay, let's move ahead. Again, some here and there questions just to understand or check your basics, whether you understand these things or not. So in linear regression, what does the term epsilon represent in the equation y equals theta naught plus theta 1x plus epsilon? So the way we generally model is we generally consider only this part for modeling purpose. Now, what is this one which we talk about? So if you have already understood the bias variance thing or reducible error, then in that case you understand that this epsilon actually represents irreducible error, because we will never be having the idealistic data. That means you are telling me that this should be the equation and I'm getting zero error in real life. That would not really be possible. So in that case, we assume an external factor, which is irreducible error, which is a random noise for us. Okay. So what is going to be the option over here, correct option over here? It's going to be residual error. Okay. And it's not reducible. We can't really avoid it. Okay. Now again, a very good question over here. So again, you have an entire big method to actually solve it. The way we actually saw over here, this equation you already aware of, x transpose x inverse, x transpose y, you can definitely use over here to find out what should be happening. And because the polynomial degree is also given to you, so in that case, you can directly use that and you can basically get the answer. Okay. So I'm not going to do that long process again. So how shall we solve this in that case? Okay. Again, see, these questions are very standard, very easy. You just need to understand what is given, think carefully, logically, and then you'll be able to solve this. So can you see over here something again? This is something closer to 2 cube. This is something directly closer to 4 cube. This is something directly closer to 6 cube. This is something closer to directly 8 cube. What is 2 cube? That's 8. What is 4 cube? 64. What is 6 cube? 216. What is 8 cube? 512. So we know that already. Now, if you see what is the difference between y and the cubes directly we are having, you'll find the number 1 here and there, and for the 8 over here we had a like a minus 2 from 512. Otherwise, you'll find for everyone it was just minus 1 every time. So what do you think should be the answer if I want to find out for 3? So in that case, you know that it should be something closer to 3 to the power 3 only, which is, I know, 27. So any number closer to 27, what do you think should be in that case? So most of the time, also check this out. What we had was, we had a 3 votes where we had like minus 1 and then 1 which was telling me minus 2. So in that case also, over here also I'll be having something less than 27 only, closer to it. So what do we think? What should be the answer? 25.9. Okay. So it's not a guesswork over here. I'm just telling you, you just verify it, but just telling you how you can approach smartly, provided you are having lesser time. Okay. Because you need not learn solving a problem. You should know how to solve a problem given constrained time. Okay. So I hope you're getting it, enjoying it. Okay. If you like the session, don't forget to like and share with your friends. Okay. Let's move further. Next question. So in polynomial regression, what is the effect of increasing the degree of the polynomial? What do we have that effect? So if I increase it, you know that I can draw the complex decision boundaries, or complex pattern can be created. That means if I increase the polynomial degree, what happens is I'll be able to capture complex patterns within my existing data. Okay. So I hope the answer we are having is very direct over here, which is going to be D. If you're having any doubt, again, you can just always comment on the YouTube or in the live class. I'll be there to help you. Okay. Let's move ahead. Seventh. Okay. Now this is I expect you to not really know most of the things, because this is a kind of going with a probabilistic idea of linear regression. Okay. Which is very rarely told, but if you have that idea, it's amazing, it's good. Okay. So just for the sake of understanding, I can just tell you right now. Okay. So maximum likelihood estimation, that's related to something, the probabilistic idea, where we are actually what do we do is we actually try to find out the parameters which maximize the chances of getting the data we are already having. So that means I'm having beta naught plus beta 1 x. Now what should be the beta naught beta 1 value from probabilistic point of view, so that I can generate the existing data? That's the idea around maximum likelihood estimation. So if you understand from the probability point of view what is the likelihood, you'll get this, that what is MLE, like by the term, what does it mean? So if you have understood that, you must be having the answer by now, that it is actually telling you that if you really want to find out the parameters, what do you try to do is you try to maximize the likelihood there of observing the data what you had. So this is going to be an answer over here. I hope you're getting. If you have any doubt, please drop a comment. Post session also, I'll be helping you out with this in case of any issue. Okay, now we are getting a little ahead. Okay, now you might feel that, oh, sir, what you're teaching, what you're asking, we have not heard about it. It's okay. If you heard about it, it's great. If not, do not worry. I'll be helping you out. Okay. So I'll give you a little context over here. So like MLE we do, MLE has a purpose in which we do not really have the idea around what can be the prior idea about my parameters. Okay. So there are two perspectives over here. My MLE, that means maximum likelihood estimation, actually talks about comes from an idea of frequentist approach. And if I talk about the map, that is coming from the Bayesian approach, where we always think about that the prior idea can always be taken to basically give the best possible parameters. So like MLE does, similarly map also does, but it always would be having some prior belief on my existing parameters, which were beta naught, beta 1, and similarly others. So the moment I'm saying what is the difference in MLE and map, MLE is just trying to maximize the likelihood to find out the best suited parameters, but map on the other hand is actually trying to maximize the likelihood of those parameters, or basically I should not say the likelihood, but it's the posterior, but it's okay just for the context right now, to increase the posterior probability or the likelihood for your sense by having an assumption or your parameters. Okay, and this directly relates to your L1 L2 regression, ridge lasso regression. So when it is ridge regression, the assumption on your parameter is that they follow Gaussian distribution. Okay, that is the prior belief we assume. And just giving you the context, if it would have been Lasso, in that case, the distribution on our parameters, which we assume as Laplace. Okay, you can just remember this. For it would just help you understand. If you do not, really do not worry, and I have just given you a context over here. You can read about it later on. But yeah, just to give you some context, that there are some techniques where we are not just doing what should I say, uh, gradient descent algorithm and all, but we use, or basically we are not just using the calculus, we are using the probabilistic idea over here to basically maximize the probability of having the data we are already having by finding out what should be the best suited parameters. Map assumes some prior belief, and over here prior belief means what is going to be the distribution of my parameters which I'm finding out. Okay, so I hope this is clear, giving you some good context over here. Let's move on ahead. So by now it must be clear, I have already given you the context. It says that if the prior is beta coming from your normal distribution, so the same thing, I told you that if beta is coming from the normal distribution, similar to the previous one, but just adding on to the same thing, in that case, what we are doing is to the objective function or to the loss function, what do we add? With beta coming from the Gaussian distribution, we are adding our ridge regularization. We are doing ridge regression, L2 regularization we are going to do. So the answer in this case is going to be C. I hope you're understanding. As I mentioned, in case of any doubt, please reach out. Okay, again, a very good question. In linear regression, our hypothesis is this: data is given, the cost function is this, m is the number of training data point, theta value already given. What is the value of j theta? You just need to find it out. So what you need to do is, and it's for practice, so please solve it up. So what you need to do is, in case you understand that, okay, this is what I'm having, you can just add on hx over here. What you'll be having is 1, 10 plus 1, 11, 3 plus 1, 4, 6 plus 1, 7, 8 plus 1, 9. So you can see what are the hx value. And what you need to do is, you can see directly over here. So it's 11 minus 5 square plus 4 minus 3 square plus 7 minus 7 square plus 9 minus 6 square, divide by what? How many we are having? 2m. So how many data points we have? 4, and 4 into 2, 8. So you can just calculate it and you can get the answer. 636 plus 1 plus 0 plus 9 upon 8, making it 45 by 8, 5 point, is it going to be 5.75, something like something, or is it something else? So we're getting 37 plus 9. Oh, sorry, my bad. It's 46. Yeah, 46. So in that case, we'll be getting 5.75. Yeah. So we have B as the correct answer. I hope you could understand. A very simple question. Cool. Let's move ahead to the next question, what we are having. A very simple question, but people generally forget about it. The parameters obtained in the linear regression, like what exactly is the range for that? Do we have a range? Are they strictly integers? Do they lie between 0 to 1, or they take only non-zero values? Is it so? So the idea is they do not really take integers, they take the real numbers. But is it between 0 to 1 only? Can't it be more than that? Yes, it can be. Can't it ever take zero value? That is also wrong, because some of the times my my bias can be 0, or like let me just write it up. So if I'm having something like that, this, let's suppose theta 0 plus theta 1 x1 plus theta 2 x2, Okay, and let's suppose I knew that x1 and x2 were very closely related to each other. In that case, I might get might I'm saying only I might get is that one of the feature might get cancelled because they were directly related, and that's what you should also be doing. Okay, to understand, like you can just think about the multicollinearity, which is one of the assumptions we are having. So we try to avoid that, but if we are not able to, in that case, that would come up, and for the feature importance purpose, it can really mess it up. But sometimes you can see either theta 1, theta 2 would be balanced over here, or theta 1 would be more than theta 2 might be more than theta 1, or 1 can be 0 if they were like correlated x1 and x2. Okay, so what do I mean by this is sometimes what you might have is some of these theta value can be also 0. So that means it's the real number, not necessarily between 0 to 1, and it can take 0 value. That means A is the correct option. I hope you could understand. Cool. Let's proceed further. Let's look at the next question. Something on the regularization, very important, very simple. Okay. So if I just talk about this, what exactly is this all about? So you already must be having some idea that why do we use the regularization, and the moment I'm saying regularization, it is very important that which regularization method has to be used in what kind of scenarios. Okay, so if I just go by this first one, which is my ohm one, let me just call it ohm one over here, or the what do we call, like I can't recall the symbol name, but let me just say ohm one over here. Okay, so if I'm just saying that, or I guess I can call it theta as well, small theta, is it? Okay, whatever. So this is actually talking about L1 regularization, this is talking about L2 regularization. And I hope you know that for L2 regularization, what is the intent? To shrink the weights, to shrink at a large scale. Okay. And for L1, also you really want to, give less, basically keep your weights in small number. Basically, you want the scale for them to be smaller. But L1 actually make your weights 0, giving you sparse weights. So that means L2 would be giving you shrinked weights as compared to L1. And L1, what does it do? It would make some of the weights 0 even. Okay. So whenever you need sparse weights, it has to be L1 regularization you shall be going with. Okay. So this is the correct option over here. I hope you're understanding. Thank you, Rihanna, Ananya. Okay. I hope Rihanna, whatever, if you're understanding, it's great. If you feel any difficulty, do comment. I'll be able to help you. Okay, I'll be there to help you. Cool. Let's proceed further. Let's just go by the next question. What do we have? I already gave, so something like this you have already seen. Now the idea is whether you have understood it or not. The solution of the following L1 regularized least square regression is this one. What? So we have this as the optimization problem to be solved. And this is the objective function with L1 regularization. Do we have a normal form solution to that? We don't have. We just talked about this when we were presenting the cheat sheet. So that means we do not really have a closed form solution. A is generally for the simple linear regression. B is for L2 regression. What about the C option? The objective is unbounded. Is it? No. We can always limit it up. Okay. So the answer to this is going to be simply D. I hope you're able to relate what I'm talking about. If not, you can always comment and understand what exactly is the correct reason to for this particular option. Let's move ahead. Let's talk about the next question. So logistic regression assumes a linear relationship between, very important question. These are not just checking your understanding, these are checking your, what should I say, like insight deep into the concept. Do you know them or not? So it's not just testing what you just know. Can you articulate those things to yourself in a better way? Can you use that to come up with some complicated question when being asked? Okay. So logistic regression assumes a linear relationship between what? Predicted variable that are continuous. So do we have a predictor variables which are continuous? Okay. Or and the response variable, what is the response variable, what is the predictor variable? I hope you have the idea. If not, we'll talk about that. Okay. Continuous predictor variables and the logit of the response variable. Now, what is this logic? I'll talk about that if you don't know, but I have talked about that within the cheat sheet already. Okay. Two predictor variables that need not be continuous. Okay, God knows. Like just giving the context for understanding. Like so, what exactly is the correct option over here? Now, what are predictor variables? These are independent variables which you consider. Okay, and those are going to be generally continuous. Generally, when you're having a classification problem, you might get some categorical as well, but the target variable would always be categorical because you need to classify using logistic regression. Okay, so predicted variable are going to be continuous. Yeah, that's fine, but like, are we finding a relationship between within those independent variables? No. Predictor variable and response variable seems correct. Seems okay. Is it? The answer is no. Why? We have a better option, better answer, which is going to tell me that okay, what exactly is happening. So this third option, if you understand, continuous predictor variables and the logit of response variable. Okay. So I hope you remember we actually wrote something like this in the beginning. Log of p upon 1 minus p equals beta naught plus beta 1 x1. Something like this. Okay. I hope you understand. So that means if I just write it up in like a proper format, so y being my class variable, I would be writing it like this. Okay. So the actual answer is that it is actually determining the relationship between the continuous predicted variables, which are like x or x's, and the logit. This is kind of logit function of the response variable we are going to have. Okay. So I hope you could understand. I hope it is clear. Sorry, this is yeah, I'm clear. So if you have any issue, please let me know in case of any doubt. Let's move ahead. I hope you're getting. Welcome, guys. Welcome. Again, very interesting problem over here. So it is again from the logistic regression. In a binary classification scenario, where x is the independent variable and y is the dependent variable you are having, logistic regression assumes the conditional distribution y given x follows what? What kind of a distribution we are talking about? Think about this. Is it an exponential distribution? Is it a normal, binomial, Bernoulli? What kind of distribution it is? So we know for the logistic regression, we have only two classes and we are finding out 0 and 1 only, kind of. Okay. So it's like I'm finding out the probability of success or failure. Two possible outcomes, just testing it out. What is the distribution? What comes to your mind? If you have studied probability properly, the distributions, in that case, it must be clear. And the subsequent question actually talks about the same thing. Test you on the same thing in a different manner. So what is it? It is going to be Bernoulli distribution. Okay. So how do we write the probability in a Bernoulli distribution? I hope you remember. So probability of a success or something like that, if you are already having. So we generally write it like this. Like if I'm having a random variable, let's suppose it's, what should I say? R. In that case, we write it like this. So this is probability of success, like the way we actually, like we generally have the answer already. Probability of R equals 1. If something like this I'm talking about, probability of success, if you know, that's P, and probability of failure is going to be 1 minus P. The way we write is something like this. Now, if I'm talking about probability of success, R would be 1. So it's P, 1 minus P to the power this. So if I say R equals 1, 1 minus 1, 0. So I'll be having P. Probability of failure, or the other class, if I'm talking about, in that case, R would be 0. This would be 0. This would be like cancelled, and not cancelled. It would be P to the power 0, giving me 1. And I'll be having 1 minus P. Makes sense. So that is the kind of Bernoulli distribution we are having, and that's how we write it. And it actually follows that only. The conditional distribution would follow a Bernoulli distribution. Okay, because I'm having only two outputs, which I'm actually looking for every time. So as I mentioned, on a similar line, I'm already having this. In logistic regression, we learn the conditional distribution, where y is the class label and x is the data point. X is the output of the logistic regression. X is the output. So that means it is giving me the probability for a particular class. Then what is going to be P of y given x? So as I told you in the previous one, what should it be? It should be something on the same node. So that means if I'm just trying to represent hx by P, what I left was P to the power R was there, but you can go by this. It should be something like this. So what you can conclude? What is a similar one? Is it C or A? It's A. Okay. I hope you got this. In case of an issue, you can always comment down. I'll help you. Okay, so let's move ahead. Let's talk about the other set of questions we are having in line. Again, interesting problem. So what we are having is a problem on, again, the logistic regression. So h of theta x, so this is the logit function we are having. So that means it has to be written like this: 1 upon 1 plus e to the power minus of theta naught plus theta 1x1 plus theta 2x2. Okay, something like this. That's our hypothesis function we are having already. Now this is given that we are having theta naught equals 6, theta 1 equals 0, and theta 2 equals minus 1. So that means it makes it 1 upon 1 plus e to the power minus 6, and theta 2 is minus 1. So it would become plus x2, and theta 1 is already 0. So this is what we are having, minus 6 plus x2. So which of the following represents the decision boundary for h theta x? What do you think? So we are having x1 and x2 already over here. x1, x2, x1, x2, x1, x2. Which would be telling me that, okay, what exactly is my decision boundary over here? So decision boundary is when I'm saying that p equals 0.5, where I'm getting a probability equals 0.5. Now, if I want my probability to be 0.5, this entire value must be 0.5, because ultimately, what does this tell? This tell me probability of y given x, the same thing. So that means if I want this probability to be 0.5, this should be 0.5. Now, the moment I'm saying it has to be 0.5, this number should be 1, because 1 upon 1 plus 1 we want, 1 by 2 overall. So it has to be 1. So the moment I'm saying, that means x2 should be equal to 6, should be my decision boundary. So what is that? Where do we have that? So we have two cases over here. One is this, one is this. Now, which one is the correct one? You have a flip side as well. 1 above, 0 below, or 0 above, 1 below. How do you measure that up? A simple thing. Again, check it out. So if x2 is greater than 6, what would be happening? The moment it would be greater than 6, what is going to happen? This would be overall positive. Yeah. E to the power something bigger. That means it would reduce it. It would reduce it. That means giving you a lesser probability than 0.5. So if x2 is greater than 6, what is going to happen? X2 is greater than 6, it would be e to the power something positive. That means it is greater than 1 over here. In that case, I'm getting bigger number than 2. It is reducing. In that case, P is going to be less than 0.5. If x2 is less than 6, what would be happening in that case? If it is less than 6, I'll be getting a minus number. So overall, I'll be getting over here as a number smaller than 1. If this number is smaller than 1, overall probability would be less than, this would be less than 1. This number would be less than 2. Overall, this probability would be greater than 0.5. So what we can really infer from here. So when x2 is greater than 6, it should be my probability is actually reducing. Now, when my probability is reducing, what does that mean? What is the class? What is going to be the class in that case? So I would always say that what actually we try to find is, I'm always finding out what is this probability. I hope you know. This is what we actually try to find out. That means probability of 1 we always try to find out. So that means if I'm saying that this if this is happening, in that case, what we are saying is the probability of saying it is 1 is lesser. That means probability of saying it's 0 is more. So hence, this is going to be the answer. I hope you could understand. In case of, again, doubt, please reach out and help yourself. So you can just infer very beautifully over here, very easily, that if x2 had been greater than 6, p is less than 0.5. And P is always talking about probability of it being 1. So if that is less than 0.5, in that case, I'm saying probability of saying it 0 is more. Okay. So B is the correct answer. Cool. Let's go to the next question. Oh. Again, simple question. You just need to understand. Please don't mind the way screenshots are cut, as I mentioned, from variety of places these have been taken for you guys, especially curated. So in the exam passing example, what is the probability of passing a student? So over here we are seeing that, okay, based on the number of hours a student study, we would like to determine what is going to be the probability of someone passing the exam. Okay. So you can see over here, this is the variable I'm having. So this is the already known logic function we are having, or segment function. In that case, you can just write it like this, just to understand, where x is telling you the study hours. So it is on a similar line as the previous one, but we are calculating something different. We are not doing the same thing. So if x is the study hours, which is given to be 4.5 hours, you need to give the correct answer again. Okay. Always remember, you should have a sanity check in your mind. I would not really be solving. It's an exercise for you. You have a calculator with you. You have everything. You just need to find out. You just need to calculate. Just put these value over here and you'll be getting the answer. But my idea over here is not to just tell you to get the answer, but to have those sanity checks, to have that intuition that what I'm doing is correct, what I'm getting is correct as well. So just think about this. We just discussed the previous problem, which was on the similar line. So this was actually telling me, yeah. So we had this equation like this. So I knew on x2 I had a boundary, and how to decide that was clear, that this I just need to check if x2 is greater than 6 or less than 6. On a similar fashion, if I am saying I'm actually finding out the what should I say, probability of passing it, I shall be getting whatever I'm having shall be greater than this or less than. I hope you're getting. It should be greater or less than to find to basically understand that whether I'm going to fail or pass. So the moment you understand that, you would be confirming yourself that, okay, whatever I'm doing is actually correct. So now you can just put it up. 4.5 into 2, 9 minus 4. 9 minus 5 is 4. So what you're going to have in the denominator is something like this. So what you're going to have is this value. I hope you're getting 4.5 into 2. You're getting 9, and then minus 5 is 4. So this is what you're getting. Now, what is going to be the probability of passing it up? You can find it out with this one. Very simple. You have the calculator, do it up, you'll get the answer. Okay. So I hope the idea is clear. On a similar note, we have one more, that if you really want to have, how many hours must a student study to have a probability of greater than 90% of passing? So what shall be that in that case? Just greater than 90%. What shall be the idea over here? 2.6, 5.8, 4.5, 3.6. On a similar line, what we did over here, not exactly just putting up the values, but you need to just use these two, the previously solved problem, to actually solve it up, and then you are done with this. I hope you're understanding what we need to find: a decision boundary, a proper decision boundary over here. Not a decision boundary. Basically, you need to just get that, okay, the probability you must be getting is around 0.9. Okay. I hope I'm clear. In case of any issue, please help me out or help yourself out. So that was all. Yeah, I guess we have one less problem today, but it's okay. I can share the another, like, I'll increase one extra problem in the next day's problems. Okay. So that was all for today from my side. In case of any issue, please reach out. I hope you could understand and you have understood how to like solve these problems, how these concepts are being like weaved with each other, be it the multiple regression, polynomial regression, linear regression, and all those things. Okay. So that was all from the problem solving perspective. Now the next part, as I promised, we'll be talking about the guidance or mentorship. So today, like, I'll just take just 5 to 10 minutes only, and then we'll wrap it up. Okay. So with respect to this thing, what I want to say is, okay, so for machine learning or basically these problems, you might get very difficult questions as well. Okay. But remember one idea: there would always be difficult questions, but the probability of those being asked would be very, very less. Plus, the probability of solving those problem by someone would also be very, very less. So please remember, what you need to take care of is you shall be targeting good questions, not getting into like too much of difficult question. Need not really worry about those if you're not able to solve, because right now is the time of test series. If people have started the test series, in that case, if you're getting lesser marks, it's okay. Please understand why you're getting, what was the type of question asked. Is it literally a little off track from the syllabus, or is it like something I knew but I could not think? If that's the answer, that you could not think, in that case, what I would say is, please revise, understand, and then solve that question again. But if it is something you could not really hit yourself, or hit that particular concept which was required to solve that question, in that case, it's a literally a trouble. Okay. So over here, just ending this on this brief note over here, please do not worry about the problems which are really difficult if you feel like while giving you the test, but make sure you're giving your best while solving these. In case of any issue, reach out to me. You can always have a conversation if you feel like it's troubling you, you're having a panic situation. There are a lot of questions, how to do it, like what to prioritize, how to prioritize, and all that. It's completely fine. Need not worry. Okay. So that was all from me today. See you guys tomorrow with another set of questions, another lecture, another cheat sheet, and we will be talking about, as I gave you within the agenda yesterday as well, we'll be talking about the next set of problems. Okay. See you guys tomorrow. Thank you for attending this session live. See you guys tomorrow. Bye bye. Good night. Thank you guys for attending this session live.